Hi all, in the last class we have discussed the definitions of characteristic vector and characteristic values, and we have proved three equivalent statement for C to be the characteristic value of linear transformation T if C is a characteristic value of T belongs to L of V. We have shown that three equivalent conditions including this. From that we can take the last one, third one, determinant of C minus T minus Ci is equal to T minus Ci is equal to 0, or you can write this as determinant of Ci minus T, that is also gives the same thing. Now you we using this definition we could able to define the characteristic value of a matrix. If A is a matrix, then the characteristic value is defined to be C, that is nothing but A x or A alpha is equal to C alpha, where alpha not equal to 0. So this is the definition of this characteristic value and characteristic vector of a matrix A. Today we discuss, suppose we have two matrices A and B. A and B are similar matrices. We will explore the properties of these characteristic values and characteristic vectors of similar matrices. Okay, before that, in order to discuss this characteristic value, in order to estimate the characteristic value, we need to solve this equation. Okay, that means if we start with the polynomial equation, say P of x equal to determinant of T minus xi. Once you are given this T explicitly, then you can easily write the determinant of this matrix. That is, first of all, find the matrix of this T and write this matrix T minus xi and find the determinant. So this determinant is in the since all the entries of this matrix of T are known, then this is always a polynomial in X. That's why we write this as a P of X. Okay, and this polynomial is called characteristic polynomial. Characteristic polynomial of T. In the similar manner, you can define the characteristic polynomial of A, that is a determinant of A minus xi. So this determinant of this matrix is called the characteristic polynomial of A. Okay, now if you write this in order to get the characteristic values, we need to equate this polynomial to 0. Then determinant T minus xi equal to 0 will give, or the roots of that equation will give the characteristic values. So you can think of the characteristic polynomials of two similar matrices. In order to get this B and A are similar, that means this B can be written as some P inverse AP, okay, where P is invertible. That means determinant of P not equal to 0. So this is the definition of similar matrices. So we will prove that for two similar matrices, the characteristic equations or characteristic polynomials are the same. That means once you write this B, the characteristic polynomial of B as this is B minus Ci. So this is nothing but determinant of B can be replaced by P inverse AP minus Ci. Consequently, you can rewrite this as determinant of P inverse AP minus C times P inverse P. Okay, because this I can be replaced by P inverse P. Now you can think of this as determinant of this can be written as P inverse A minus C I P. Okay, so this means we can take this P inverse out from the left hand side, and you can take P out from the right hand side. Then this we can distribute this determinant using the properties of determinant. So this will be determinant of P inverse, determinant of the matrix A minus Ci, and determinant of P. Okay, since this determinant are elements of F, here the underlying field is F, then these are elements of field F, then this commute, all these three elements commute. So we can write it as that is equal to determinant of P inverse, determinant of P, then determinant of A minus Ci. Okay, now you can write this is determinant of again P inverse P, that will give determinant of I, that is equal to 1. Okay, now this reduces to determinant of A minus Ci, which shows that determinant of A minus Ci is equal to determinant of B minus Ci, which shows that determinant of the characteristic polynomial, if P is the characteristic polynomial of A, then you write determinant of A minus Xi, which is same as determinant of B minus Xi, because of this equality, and this is going to be the Q of X, the characteristic polynomial of B. Now once you are given two similar matrices, then characteristic polynomials of these two similar matrices will be the same. Therefore the characteristic equations coincides. Okay, that means characteristic equations means characteristic equation of A is determinant of this A minus Xi equal to 0. So the roots of that will be same as determinant of B minus Xi equal to 0, because these two determinants are the same. So the characteristic values of A is same as characteristic values of B. That means similar matrices have the same characteristic values. Now we can think of this these similar matrices, then characteristic values are the same, characteristic polynomials are also the same thing. Now we can discuss some examples. If you consider a matrix A that is equal to 1 0 minus 1 1 0, this is a matrix. I consider this matrix as an element of M2, this is R, so real numbers M2R. Now you consider this matrix, and this is the characteristic value of this matrix is defined to be the values of C belongs to R such that determinant of A minus Xi equal to 0, A minus Ci, or if X is the C is the characteristic value, then A minus Ci is equal to 0. To evaluate the characteristic values, we need to first you write the matrix A minus Ci, that is 0 minus 1 1 0. This is our matrix A minus C times identity matrix. The identity matrix is 1 0 0 1. Now you write this difference, that will be minus C minus 1 1, and we have minus C again here. So that will give C square plus 1. Okay, so in order to get C belongs to R such that C square plus 1 equal to so this is the determinant of all this, determinant of this thing, that will give C square plus 1. But when you equate this to 0, so then that C doesn't so we can get that C does not belong to R. Okay, this shows that there is no C belongs to R satisfying this condition, determinant of A minus Ci is equal to 0. This shows that the matrix A has no characteristic values. Okay. On the other hand, if you can consider this A is an element of M2C rather than M2R. Okay, in that case, if we consider this matrix as a element of M2C, then these complex numbers are going to be the characteristic values. That means C belongs to instead of R, we write C belongs to C such that determinant of A minus Ci equal to 0. But this would imply that C square plus 1 equal to 0. That will imply that C is equal to plus or minus 1, plus or minus I. This shows that I and minus I are the characteristic values of this matrix A belongs to M2R. That means in order to define the characteristic values, you need to specify the corresponding field, if in case of the transformation or matrix. If you consider the C, if you consider A as an element of M2C, then A possesses characteristic values. Okay, and consequently characteristic vectors as well. Otherwise, if we consider these matrices are elements of this matrix is an element of M2R, then you can never get a characteristic value. Okay, but because any C belongs to R does not satisfy this condition. Okay, so it shows that there is please note it as a remark, in order to discuss the characteristic value you need to specify the corresponding field or underlying field. Okay, if fields are different, then the nature or behavior of the characteristic values will be changed. Now we discuss another example. Say A is equal to the matrix 1 2 0 3. This belongs to M2R again, and once you write the characteristic polynomial of this, you can get determinant of A minus xi equal to 0. That would imply that this determinant of A minus xi is 1 2 0 3. This is A, minus xi is x0 0 x. Okay, so this will be 0. Then that would imply that the determinant of the matrix 1 minus x 2 0 here, 3 minus x, the determinant of this matrix equal to 0. Consequently you can get 1 minus x times 3 minus x equal to 0. So this implies x equal to 1 or x equal to 3. This shows that there are two values for this x which satisfies this condition, determinant of A minus xi equal to 0. So the characteristic values are, then we can write characteristic values are 1 or 1 and 3. So these are the characteristic values. Now we will find out the corresponding characteristic vectors of this. So in order to find out the characteristic vectors, we need to solve the equation Ax. We need to find out x not equal to 0 such that Ax equal to Cx if C is the characteristic value. So this implies set of all x not equal to 0. This is the characteristic vector x not equal to 0 such that A minus Ci times x equal to 0. Okay, so these collections are called the characteristic vectors. So we will write out all the characteristic vectors x not equal to 0 such that this happens, A minus Ci of or times x equal to 0. From this set you can choose characteristic vectors. So the characteristic vectors need not be unique, that there may be more than one characteristic vector. So in order to get, you need to find out this collection, and of course this x equal to 0 satisfies this condition as well. So once you write the set of all x such that, or x belongs to the corresponding that field, not field, x belongs to corresponding vector space, or in this case we write that is set of all x belongs to R2 such that that means in that sense we write it as set of all x takes the form xy belongs to R2 such that this happens. Okay, that means A minus Ci of times x equal to 0. From this collection you can choose non-zero elements. Those non-zero elements will be the characteristic vector corresponding to the C. So in order to get the characteristic vector corresponding to 1, we need to find out the set or the solution space of this equation, that is x set of all x y such that xy belongs to R2 such that A minus I, C is 1 here, times x equal to 0. We need to find out the set first. This is the characteristic, and this is called the characteristic space. Characteristic space corresponding to or associated with, corresponding to C is equal to 1, or the characteristic space associated with the C is equal to 1. Okay, so if you C is a characteristic value, this is always a this is always called a characteristic space, because once you have take x1 x2 belongs to the characteristic space characteristic space corresponding to C, then you can get this Tx1 or Ax1 equal to Cx1 and x1 not equal to 0. And similarly, if you are restricting, if you are not restricting x1 not equal to 0, you can think of this is the characteristic space. In fact, this contains 0 vector as well. So we didn't restrict our discussion to this non-zero elements. So we collect all such x satisfying this. So if you choose two of them, arbitrary two of them, then ax2 is equal to cx2. So consequently, you can get a times x1 plus x2 will be c times x1 plus x2. That means this x1 plus x2 is also a member of this collection, okay, or this collection. This is our general case. And if you choose a times cx1, that is nothing but c times ax1, or write it as k times a of k times x1 will be k times a of x1, that is equal to k x1 is equal to c times x1. So you can write it as c times k x1, which shows that whenever we take an element x1 belongs to this set and write a times kx1 is equal to c times kx1, which shows that this kx1 is also a solution of this part. Okay, so then kx1 is also an element of this. So which shows that this is always a subspace. Okay, subspace of V, or in this case R2. Then that subspace is called characteristic space corresponding to C. Okay, now you will find the characteristic space corresponding to 1 here. How will you find out the characteristic space? You need to find out the solution space of this equation. So we know that in this case A is 1, 2, 0, 3 and I is 1, 0, 0, 1, and we have this minus this times x, that is x, y equal to 0. 0 means the vector 0, 0 or the matrix 0, 0. So that will give by subtracting this, you can get that matrix as 0, 2, 0, 2 times x, y equal to 0, 0. So by solving this, you can get the characteristic space or set of all x satisfying x equal to 1 into x. So that will give the characteristic space defined in this set, defined as this set. Now how to get the solution space of this? In order to get the solution space, we will think of this matrix as the coefficient matrix, and this is unknown. Okay, and this is a homogeneous system of equation. We know that if every homogeneous system is consistent, then it has solutions. Okay, now we are going to write out all the solutions of this. So first you write the rank of this. If A is equal to 0 to 0, 2, then rank of A is 1, because these two rows are same rows, or that is a the rank of these two rank of this matrix will be 1, and in that case we need to write out that means from this you can get only one independent equation, say 2y is equal to 0. From this you can write y is equal to 0. Consequently, whatever be this x, we can get this equation. Okay, which shows that if you write x equal to xy such that belongs to R square, such that y equal to 0, that is the only possible quantity from this part. Okay, so y equal to 0. So this is the characteristic space corresponding to lambda c is equal to 1. From that means set of all here y equal to 0, set of all x 0 such that x belongs to R is the characteristic space corresponding to C is equal to 1. Okay, now from this you can find out all the characteristic vectors. If x not equal, any non-zero element of the set will give the characteristic vectors. So we have, right, this is the characteristic vector there are so many characteristic vectors are there. Anyway, any non-zero quantity from this set will be the characteristic vector corresponding to C equal to 1. In the similar way, you can think of the characteristic vector character space corresponding to C equal to 3 by replacing this C by 3. Now, in that case, you will get A minus 3i, and we have to solve this A minus 3i here and find out the rank of this. Okay, the rank of this matrix should be less than n, less than 2 in this case, because we have calculated the C in such a way that determinant of this A minus Ci equal to 0. That means when you put the value C either 1 or 3, you can get determinant of this is 0. That means it shouldn't have n linearly independent rows. That means the rank never be 2 in this case. Okay, in this case rank will be 1. Okay, so rank is always less than n in general case. Now in the similar way, you can think of the matrix T A minus 3i and find out the solution space of this equation. That will give the characteristic space corresponding to C equal to 3.